Hello, can you hear me? Testing. I'm testing my volume. Testing. Okay, the stream is now on. Okay. Hello, everyone. So I'm going to be studying discrete math again. Let me change to full screen. Okay. This was from last stream. Right. So I studied just the introductory stuff. This time I'll start with logic and proofs. Mathematical statements. While walking through a fictional forest, you encounter three trolls guarding a bridge. Each is either a knight who always tells the truth, a knight always tells the truth, always truth, uh, or a knave who always lies. What's a knave? A knight. Actually, don't know what a knave is. A knave always lies, and or a knave who always lies. The trolls will not let you pass until you correctly identify each as either a knight or a knave. Each troll makes a single statement. Oh, so there are three of them, and each one is either a knight or a knave. Two, three. If I am a knave, then there are exactly two knights here. Troll one is lying. Then either we are all knave or at least one of us is a knight. Which troll is which? So troll one, two, three. This is going to take quite some time. True, false. Okay, let's start with all false. False, false, true. True and true. And then all this, it repeats. True, 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 true. Yeah, how do we find which one is which? Always truth, always lies. I think we need to find out if there's a contradiction with each one. So if all of them are liars, if each statement is false, either we are all knaves or at least one of us is a knight. What's the negation of this? Either we are all knaves or at least one of us is a knight. Wait, what's the negation of this? So if this guy was a knave, if troll 3 was a knave, and if he's lying, then what's the truth version of this? Troll 3 cannot be a knave, right? It's not possible. This statement has to be true. Okay. It's in this. What about this over here? If I am a knave, then there are exactly two knights here. Okay, let's assume that these two are false. Um, if I am a knave, then then there are exactly two knights here. If both of them are lying, then both of them are knaves, right? But then there's a contradiction over here. If this guy is a knave, then troll 1 is telling the truth, but troll 1 is also a knave. So they can't both be knaves, right? Why does this keep popping up? Uh, let's see. We are left with these three. False, true, 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 false, true, and true, true, true. Okay, let's try this. False, true, true. This guy is lying and this guy is telling the truth. If this guy is telling the truth, then this guy is lying. That holds up. If I'm a knave, then there are exactly two knights here. But if he's wrong, then there are not exactly two knights here. But we know that these two are knights. So there's a contradiction. So we can't have this either. True, false, true. If he's telling the truth, if I'm a knave, then there are exactly two knights here. That this is if he's a knave. If he's a knight, then that doesn't tell us anything. So troll 1 is lying. So this guy is lying. So troll 1 is telling the truth. This is so knight, knave, knight. But since he's a knight, uh, his statement doesn't mean anything. Statement only has a meaning if he's a knave. Okay, this part holds up. What about true, true, true? So if this is true, then he's a knight. He's a knight. He's a knight. But troll 1 is lying, and that's a contradiction. So I'm guessing true. So knight, knave, knight. In order to do mathematics, we must be able to talk and write about mathematics. Perhaps your experience with mathematics so far has mostly involved finding numerical answers to problems. As we embark towards more advanced and abstract mathematics, writing will play a more prominent role in the mathematical process. In fact, the primary goal of mathematics as an academic disciple in its own right is to establish general mathematical truths. How can we know whether these facts, perhaps called theorems or propositions, are true? We construct valid arguments called proofs, which establish the truth of the statement. Here, an argument is not the sort of thing you have with your mom when you disagree about what you have for dinner. So, definition, argument. An argument is a sequence of statements, the last of which is called a conclusion, the rest of which is called premises. An argument is said to be valid provided the conclusion must be true whenever the premises are all true. Argument is invalid if it is not valid. That is, all premises can be true and the conclusion can still be false. An argument is sound provided it is valid and all premises are true. A proof of a statement is a sound argument whose conclusion is, is the statement. To determine whether we have a proof of a statement, we must decide both whether every premise is true and whether the argument is valid, whether the conclusion follows from the premises. How can we do this? Consider the following two arguments. If Edith eats her vegetables, then she can have a cookie. Edith eats her vegetable, Edith gets a cookie. Florence must eat her vegetables to get cookies. Florence eats her vegetables. Florence gets a cookie. This symbol means therefore. Are these arguments valid? The first one definitely is. So the two arguments look almost identical. Eden and Flora both eat their vegetable. In both cases, there's a connection between eating the vegetable and cookies. Yet we claim that it is valid to conclude that Eden gets a cookie, but not that Florence does. The difference must be in the connection between eating vegetables and getting cookies. You need to be skilled at reading and comprehending these statements. Do the two sentences mean the same thing? Unfortunately, in everyday language, we are often sloppy and you might be tempted to say that they are equivalent. But notice that you just because, yeah, it says Florence must eat her vegetable to get a cookie. Just because Florence ate her vegetable doesn't mean she will necessarily. Wait, wait. Just because Florence ate her vegetables doesn't mean she will necessarily get the cookie, I think. Like she has the option to get the cookie now, but that doesn't necessarily mean she gets the cookie. Florence must eat her vegetables. We have not claimed that doing so would be enough. She might also need to clean her room. For example, in everyday practice, you might be tempted to say this other direction is implied. In mathematics, we never get that luxury. Since arguments are built up of statements, we must agree on what counts as a statement. A statement is a declarative sentence that is either true or false. If the sentences in an argument could not be true or false, there would be no way to determine whether the argument was valid, since validity describes a relationship between truth values of the premises and conclusions. The goal of this section is to explore different shapes a statement can take. We will see that more complicated statements can build up from simpler ones in ways that entirely determine their truth value based on the truth value of their parts. While reading on to the main content of this section, complete this preview activity to start thinking about the types of questions this section will address. Which of the following sentences should count as a statement? That is, which of these statements below could you potentially claim the sentence was either true or false? Select all that applies. Uh, this could be either true or false. This is true or false. This. Oh no, not C. C was wrong. You, you and your roommate are arguing. And they're making the audacious claim that pineapple is both good in pizza and in smoothies. Which of the following are reasonable responses to this claim from a logical point of view? The statement is false because everyone who likes pineapple on pizza does not like pineapple in smoothies. Which of the following are reasonable responses to this claim from a logical point of view? Pineapple is good both on pizzas and in smoothies. The statement is false because everyone who likes pineapple on pizza does not like pineapple in smoothies. Okay. Yeah, then you can't make the claim that pineapple is both good on pizza and smoothies. The statement is false because while pineapple is good in pizza, pineapple is good in smoothies. A pizza smoothie is never good. I don't think this claim makes sense. Statement is half true because regardless of what you think about pineapple on pizza, we can all agree that it is pineapple on good on smoothies. I don't think this is correct. The statement is false because even though pineapple is good in smoothies, it is not good on pizzas. Yeah, because you wrote and over here. And means they both have to be true. When if one of them is false, then this entire statement is false. Your roommate now makes an even more outrageous claim. If a superhero movie is part of the MCU, then it is good. Which of the following are reasonable responses to this claim from a logical point of view? Statement is false because, for example, Green Lantern is neither Marvel nor good. No, the claim is about MCU, so we talk about Marvel only. Statement is false because there is at least one superhero movie that is part of the MCU that is also not good, so this makes sense. Uh, there are good superhero movies that are based on DC, so not no. This statement is not a correct counter for this. Your roommate won't let your roommate just won't let up with their outrageous claim. Now they claim that either every troll is a knave or at least there's one troll that is a knight. What can you say? Statement is false because no troll could say that all trolls are knaves since knaves always lie. Every troll is a knave or at least one troll is a knight. This is false because some trolls are knight and some trolls are knave. Okay. Statement is false because there is no way to verify which of the two options is the case. And you can verify it. You can ask one troll whether the other troll is a knight. Maybe. Yes, this is true because every troll is either a knight or a knave. If it is not the case that all trolls are knaves, then there must be maybe. Okay, D is correct. This is false because some trolls are knights and some trolls are knaves. They claim that either every troll is a knave or there is at least one troll that is a knight. Oh no, then it's not false, right? Atomic and molecular statements. A statement is any declarative sentence which is either true or false. A statement is atomic if it cannot be divided into smaller statements, otherwise, it is called molecular. These are statements, in fact, atomic statements. Telephone numbers in the USA have 10 digits. The moon is made of cheese. 42 is a perfect square. These are not statements. Would you like some cakes? The sum of two squares. Go to your room. I want to see examples of molecular statements. The reason the sentence 3 plus x is equal to 12 is not a statement is that it contains a variable. Depending on what x is, the statement is either true or false. But right now, it is neither. One way to make the sentence into a statement is to specify the value of the variable in some way. This can be done by setting a specific substitution. For example, 3 plus x is equal to 12 where x is equal to 9, which is a true statement. Or you could capture the free variable quantifying over it for it, as in for all values of x, 3 plus x is 12, which is false. You can build more complicated statements out of simpler uh, ones using logical connectives. For example, this is a molecular statement. Telephone numbers in the USA have 10 digits and 42 is a perfect square. Now that we can break this down into two smaller statements, the two shorter statements are connected by an and. We'll consider five connectives: and, or, if then, if and only if, and not. The first four are called binary because they connect two statements, while not is called a unary connector. These molecular statements, of course, still statements, so they must be either true or false. The crucial observation here is that which truth value the molecular statements achieves is completely determined by the type of connective and the truth value and the truth value of the paths. You do not need to know what the paths actually say or whether they have some material connection to each other. To analyze logical connectives, it is enough to consider propositional variables, sometimes called sentinel variables, usually capital letters in the middle of the alphabet. A, Q, R, S. We can think of these as standing in for usually atomic statements, but there are only two values the variables can achieve, true or false. We can also have symbols for logical connectives. So, and, well, this looks like an A. We have or, which is an upside down and. We have implies, if and only if, and not. And then we have a binary. So, and, or, implies, if and only if, not. Um, I have some issue with this one over here. Implies. Like I never understood. So P Q P implies Q. True, true, false. Actually, let's just do ones and zeros from now onwards. Mm, 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 mm. Okay, so for this statement, for someone to say that P implies Q, for example, event P, like I click a button, like you click a button and then a light shines. You click this button and then this lights up. So whenever you click this button, this will light up. For me to say that clicking this button lights this up, if P then Q, this has to be true, that this is true, and then this is true. This has to be true, that if this doesn't light up, you didn't press the button. Because if this is lighting up and the button is not pressed, wait, yeah, that this is not lit up, then that means the button is not pressed. Because if this uh, is not lit up and the button is pressed, then we cannot make this claim. So when someone says P, if P then Q, we expect this, and not this and not this. But these two statements, you have a problem. Let's see. So if I press P and then Q doesn't lit up, then P doesn't imply Q. So this, so P implying Q means this is true, and that this is false. And then this last statement is the issue I have. That if you do not press P, then Q can either happen or not happen. It shouldn't matter because there could be a third event. Let's call this event M, which could also light up this button. So over here it says true. But the thing is, in our everyday language, like even if this part is false, we would still say P implies Q. We would still say if P then Q. For example, if this is 0, if this is 0, the button is not pressed, and then this doesn't light up. Sorry, the button is not pressed, and then this lights up. Wait, I'm getting confused. Okay, I will get back to this. I need to clarify what I mean. I don't think we focus on this part when we talk about if statements. For example, we can use the truth table for P implies Q to decide whether if 5 is even, then 6 is even, is true or false. Here, P is a statement, 5 is even, and Q is a statement, 6 is even. Since 5 is not even, the statement P is false. The statement Q is true. The truth table tells us that P implies Q is true whenever P is false and Q is true. So the statement if 5 is even, then 6 is even is true. If you don't like that the statement is true, hold on to that thought. We will hopefully resolve it soon. 8. Uh, since 5 is not even, then the statement P is false. Since 6 is even, then the statement Q is true. The truth table tells us that P implies Q is true when P is false and Q is true. So this statement is true. If you don't like the statement, if you don't like that the statement is true, hold on to that thought. Okay, yeah, this is the problem I was having. Now that for us, or is inclusive or, and not the sometimes used exclusive or, meaning P or Q is true when P or Q or both P and Q are true. Okay, so there is the normal or and exclusive or. Wait, let me copy paste this. So and is like this, or is like this. And then we have, I think XOR is like this. So or is either one of them is true. So one, one, one. XOR is like only one of them is true. They can't be both true. This. Wait. No, no, no. Hold on. Is this correct? Yeah, yeah, yeah. I think this is correct. As for this is true when P or Q or both P and Q are true. As for other connectives and behaves as you would expect. Okay. This leaves only the implication, which has slightly different meaning in mathematics than in ordinary usage. However, implications are so common and useful in mathematics, we must develop a level of fluency with their use, which warrants a whole section. Using truth conditions for logical connectives determine which statements below are true and which are false. 17 is prime and 17 is odd. Okay, let's just skip this. The way we define logical connectives and their truth value is very precise and technical. Often, language is not part of learning how to communicate. Mathematics is learning how the cultural norms of mathematical language and how to translate statements in ordinary language into these technical statements. This will get easier in practice, so make sure you are talking to lots of people about the math you are studying. Identify the logical structures of each of the following statements. 4 and 5 are both prime. Only one of 4 or 5 is prime. Did you know that all mammals have hair? That every integer is even or odd? That some odd numbers are not prime? Our goal is to explore how to write statements such as these in mathematical notation to highlight the logical structure of the statement. So over here, what we had to do was like P and Q. P is 4. No, no. P is 4 is prime and Q is 5 is prime. And then we write P and Q. Over here, we do P exclusive or with 5. You must attend every day and do the homework to pass this class. So passing this class means it should be if attend every day and do homework, then pass the class. If you pass the class, then it must be the case that you attended every day and you did the homework. Shouldn't it be the opposite? If you attended every class and you did the homework, then you pass the class. Hold on. This is true. Sorry. And then 1, 1, 1, 0. Yeah, so let's say Q. Q is attending every day and doing the homework. This entire statement will be Q. If Q is true, then you pass the class. This is false. This cannot happen. But this is true. It's this part that is confusing me. Q doesn't happen, but P happens. Then this statement is true. And for P implies Q, P doesn't happen, but Q happens. But we still say P implies Q. It is possible that there are other things that's letting Q to happen. So for example, for this button and light thingy, P doesn't happen, but Q happens. That could be because some other button was pressed that switches on Q. So Q being for P being false and Q being true. So P implies Q is still possible, right? But this should be 1 or 0. Like this should be undefined. It should only be these three statements, not this fourth one. Because either of them is true. Because if P doesn't happen, whether Q happens or not, you would still say if P then Q. Like let's say, let's say these three statements holds up. Now let's say P doesn't happen, but Q does happen. Whether uh yeah, you would still, this can either be true or false, right? Like if P doesn't happen but Q happens, okay, never mind. So universal quantifier is written with upside down A, red for all. Existing quantifier is written with a reverse E. Is red, they exist. So I still don't understand why they phrase it like this. Every number is even or odd. So that would be written like, let P be that that a number is even, Q be that a number is odd. For every X, either X is even or X is odd. X even or X odd. Or you write it like this. Now E is they exist. I should have written for all. This will require considering a few sort of basic sentence called a predicate, which is like a statement but contains a free variable. When you replace that variable with a constant of some sort, then the statement becomes a statement proper. Think of a predicate as making a claim about values that are substituted for placeholder variables. A predicate can be made into true or false by evaluating it at some constants, or we can claim that some or all possible constants would make the resulting statement true or false. This is done using quantifiers. We usually write predicates similar to how you write a function, although with capital letters. For example, we might use the predicate px to represent x is prime. We can say p7 is true since 7 is prime, and that p8 is false. Or using quantifiers, we can falsely claim that all numbers are prime by writing for all x px, or truthfully claim that there exists a prime by writing there exists px. Just like we did for propositional logic and logical connectives, we should decide what it means for a quantified predicate to be true or false. We say for all x px is true if pa is true no matter what constant a we substitute for x. Similarly, there exists px is true if there is at least one value a for which pa is true. You must be careful here. Consider the statement for all x there exists a y where y is less than x. You would read this for every x there is some y such that y is less than x. Note that less than is a predicate with two free variables. We have chosen to write it with a symbol between the variables instead of the funky looking lyx or less than yx. Is this statement true? The answer depends on your domain of discourse. When we say for all x, do we mean all positive integers or all real numbers or all elephants? Usually this information is supplied by the context of the statement. In discrete mathematics, we always quantify over natural numbers. So let's take that for our domain of discourse here. For the statement to be true, we need no matter what natural numbers we select for there to be some natural number that is strictly smaller. Perhaps we could let y be x minus 1, but here is a problem. What if x is equal to 0 and then y is equal to negative 1 and that is not a number in our domain of discourse? Thus, we see that the statement is false because it is a number less than or equal to all other numbers. In symbols, we have this. We will explore some rules for working with quantifiers, some other connectives in section 1.3. For now, we will mention in ordinary language and a more precise language of logic. There is no perfect algorithm for doing this translation, but here are a few useful rules of thumbs. Any statement of the form every p thing is a q thing can be written as for all x p then q. All mammals have hair becomes for all x. If x is a mammal, then x has hair, where m means x is a mammal and h means x has hair. Make sense of this? Think about what we mean by statements like these in terms of sets. We claim that the set of mammals is contained in or is a subset of the set of hairy things. What we mean by A is a subset of B is precisely that every element of X is an element of Y. Any statements of the form some P things or Q things can be written as so there exist P and Q. Or there exists X where X is a P and also X is Q. Why can't we do this over here? It exists in X such that if X is P, then X is Q. Why can't we do it? It is always a good idea to be precise in mathematics. Sometimes, though, we can relax a bit as long as we all agree on a convention. An example of such a convention is to assume that sentences containing predicates with free variables are intended as statements, where the variables are universally quantified. For example, you believe if a shape is a square, then it is a rectangle. But how can that be true if it is not a statement? To be a little more precise, we have two predicates. Sx for x is a square or x for x is a rectangle. Then sentence we are looking at is if x is a square, then x is a rectangle. This is neither true or false as it is not a statement. But come on, we all know what we meant to consider this. So for all x, if x is a square, then x is a rectangle. And this is what our convention tells us. We call the resulting statement universal generalization of the original statement. Given a sentence with a free variable, the universal generalization of that statement is a statement obtained by modifiers to the beginning of the sentence so that all free variables become bound. Similarly, we will often be a bit sloppy about the distinction between a predicate and a statement. For example, we might write P in B the statement. N is prime, which is technically incorrect. It is implicit that we mean that we are defining P n to be a predicate, which for each n becomes a statement. N is a prime. Symbols with its type of statement. P and Q, not P, implication, or. Which of the following statements are true about the sentence? If you substitute 10 for x, it's true. Is false since x has a free variable, I think. It's this. The universal generalization of the statement of this sentence is a statement. Yeah, yeah. What questions do you have after reading this section? Okay. What is this activate? What did I just click? For each sentence below,